We're going to take a look at our last two shortcuts for how to prove that two triangles are similar to each other. So if we recall, our definition initially for similar triangles or similar polygons in general is that all the corresponding angles are congruent, all the corresponding sides are proportional. Instead of being congruent like they would be in two congruent triangles. And so our first shortcut was angle-angle, which was essentially saying that all the corresponding angles of two triangles are congruent. And so now we have our second theorem, which is a side-side-side similarity theorem. So if the corresponding side lengths of two triangles are proportional, then the triangles are similar. So let me draw your attention to one word really quickly here, which is proportional. All the time, what we tend to say here is that the sides are similar to each other. The sides are not similar. Okay, two objects can be similar, and it's because they contain the set of properties of all the angles, corresponding angles being congruent, and then the sides being proportional. But when I'm actually talking about numbers and talking about lengths of things, they are proportional to each other because they form a ratio. So that's where we want to use. So let's take a look at this real quick. If I have a triangle again, so here's a triangle. This is triangle ABC, and I have another triangle, which is triangle DEF. All I need to know, or all I need to show that these two triangles are similar to each other, is that each pair of corresponding sides are proportional. Now the question is, how do I show that? Because normally, if I was using angle-angle, for example, I wouldn't start off by showing that angle A is congruent to angle D. But we don't have this notation for the sides being proportional, and so what we need to talk about instead is these sides being proportional, their lengths being proportional in an equation. So the thing that I need to show, the way that I'm going to write it, is that the length of AB over the length of the corresponding side, DE, is going to be equal to the length of BC over the length of EF, and then the length of AC over the length of DF. So if you remember, this is our statement of proportionality that we're essentially writing here. And what I want to do is, if I want to prove that these two triangles are similar to each other, I need to essentially prove their statement of proportionality is true. Okay, so this is the other side of things. We had the angle-angle postulate that said that if the corresponding angles are congruent to each other, or two pairs of corresponding angles are congruent to each other, then the triangles are similar. And now we're saying that if the corresponding sides, all three pairs of corresponding sides, that's why it's side, 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 all three pairs of corresponding sides are proportional to each other, then the triangles will be similar. And again, this is something that's just kind of intuitive to us. We'll justify it later when we talk about what are called dilations. But for now, we're just going to kind of accept this as true, even though it is a theorem, just because it makes sense to us. But we'll justify it later. So again, if I want to prove that two triangles are similar to each other, I just need to prove that each pair of corresponding sides are proportional. So that's way number 2 that we've seen, the first one today. And now the third one, and the second one today, is a side-angle-side similarity theorem. So this one is a little bit longer, just because we need to talk about this included angle, but it's just as easy. So it says, if an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the sides including these angles are proportional, then the triangles are similar. So the real crux of this here, the crux of this that we need to talk about is this included part. So if an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the sides including these angles are proportional. So we have to remember what this word here, including, means. We talk about, if I have a triangle and I want to talk about this angle right here, the included sides would be sides AB, this one here, and then side AC. These are the sides that include, or I shouldn't say they're included sides. They're the sides that include this angle here. So what does that look like? Let's do this one more time. So if I have two triangles, again, that are somewhat similar looking. I use those. So D, E, F, and G, H, I. If I want to say that these two triangles are similar to each other, I need to show two things. If I have a pair of corresponding angles that are congruent, so let's say I have angle D and angle G. I should have been using a different color. D and G congruent. So that's step one. Angle D is congruent to angle G. And if I also know then that the sides that include these angles are proportional, then these triangles are similar. So if DE, its length, over its corresponding length, GH, is proportional to, so equal to the ratio of DF to GI, then these two triangles are similar. So this one I actually have to show kind of two things here. I need to show this pair of angles are congruent to each other, and then the sides that include them, DE and GH, and then DF and GI, are proportional to each other. Not similar, but proportional to each other. And so that's my last way that I have, my shortcut of proving that two triangles are similar. So at this point we have angle, we have side, and we have side, which the only confusing thing here, of course, is that these sound very much like our congruence postulates or theorems that we had for proving triangles congruent, but now we're proving that triangles are similar. Instead of saying the sides are congruent to each other, we're saying the sides are proportional to each other. So, like I said, not too bad. These are just more tools that we have now available to us so that we can prove that triangles are similar.